All right, so we're looking at electrochemical cells in our second section. This is where we're using those redox reactions in the process of a battery, which is the most common use of redox reactions. There are two types of electrochemical cells. We'll focus on one in this lesson, and then the next lesson we'll focus on the second type. The first type is called a galvanic cell. You might also see it written as Voltaic cell. Those are interchangeable. It's just a system that generates electricity through the use of a spontaneous reaction. Now, a spontaneous reaction typically is exothermic, which means it would have a negative delta H. It tends to create disorder, which means it has a positive delta S value, S meaning disorder or entropy. And if we use those two concepts together, we get what's called Gibbs free energy, which is delta G. A negative delta G would be spontaneous. We're not going to do anything with the math. That is more of an HL topic than SL topic. But I wanted you to know what values we would look for a spontaneous reaction. Now, a half reaction or half cell reaction is where oxidation and reduction occur, and they occur at the electrodes, which are the solids that are in the cell. The anode is the electrode where oxidation occurs. You can use anox to remember that connection. And it is the negative side of the voltaic cell. Cathode is where reduction occurs. You can remember that because of red cat. And that is the positive side of the voltaic cell. The other part of the battery that you would need is a salt bridge, which is a hollow U-shaped tube of glass filled with an inert electrolyte. So remember, electrolyte could just be an ionic compound, inert meaning they're not going to be reactive. So typically you choose anything from group 1 as your cation, and then nitrate is always aqueous, so that a lot of times is what's used as the anion. The cation would move towards the cathode side to help build back up the positive side of the cathode. And then the negative anions move towards the anode to build or to help balance the positive charge buildup that's happening on that side of the battery. So let's take a look at a battery. Here they've told us that this side is the anode and this side is the cathode. So when we want to write the oxidation half reaction, remember that's happening on the anode side, and oxidation means the loss of electrons, which is why the electrons traveling along the wire are going away from the copper side. So between copper and copper plus 2, we have the copper forming the plus 2 ions, which would also release those 2 electrons. So because the electrons have to be lost, I know that the reaction has to be written this direction. The cathode is the side that reduction occurs on, which means you gain electrons. And so for this side, we have our silver ions gaining an electron to form the solid silver. So if we were to watch this process take place, what we would notice is that we start losing some of the mass of the copper electrode, while the silver electrode starts gaining mass. Because we're losing that solid, it's becoming a solution. Where on this side, we're gaining that solid. So this electrode will get smaller, and this electrode gets larger. To write the overall balanced reaction, we have 2 electrons and 1 electron, so we would have to multiply this side by 2. And so the overall balanced reaction then would be copper, 2 silver ions going to our copper ion, and 2 silver atoms. All right, we can also write notation for this. So instead of having to draw the battery each and every time, we can just write a notation. We use a single vertical line to show the phase boundary. So this would be between the solid and the solution. So in our last example, the solid copper and the solution of copper 2, we would just draw a single line between them. The double vertical line denotes the salt bridge. The anode is always written first, and then we write the cathode. So going back to our picture here, we have our copper electrode. Then we have our phase boundary to where it's going to form the copper ion. Sometimes you might see a concentration given there as well, but it's not always needed. Then we have the salt bridge, which is the part in between. So we're going to show that double line to show that it's a separation. Then we have our solution of silver ions. Phase boundary again between the solution and the solid. And then we have our silver. So this right here is the notation for this battery cell. Now we can also talk about the electrode potential. So voltaic cells are the spontaneous cells. Delta G, this is a typo, it should be negative. The voltage should always be a positive value, and as the voltage decreases and reaches 0, that's when your battery dies. So you have to have that positive voltage in order for the battery to be producing that electricity or that the power. To determine which two reactions give you the most positive voltage, you would add them from the section 24 of the data booklet. Now section 24 is actually on page 23, so just be careful with that numbering. Section 24 has them listed as reduction reactions. So if you have to find the value for an oxidation reaction, that means it's flipped compared to what is given on page 23. So you need to change the sign of the cell potential. All right, so if we think back to what we were doing previously, this setup, we have our copper going to copper plus 2. So if we look for this reaction on page 23, you'll notice that it is written backwards. Make sure you find the right one because there is more than one. It's written backwards, so the cell potential is not positive 34, but negative 0.34 volts. The 0 there just means it's at standard state. Then if we look for the cell potential for the silver, that one is written correctly because silver is being reduced. So all we need is the cell potential. We don't have to worry about the sign, and it's a positive 0.8 or 0.80 volts. So if we were to add those together, our cell potential would be 0.46 volts, which is what you're seeing up here in the voltmeter. So that's what that is measuring, is the cell potential based on those two half reactions. So we're going to look at this new setup. First, we want to write that balanced reaction. So we're going to look and see what's going on here. We have nickel going to nickel plus 2, which means the nickel is my oxidation half reaction because it's losing electrons. Then we have cobalt 3 plus going to solid cobalt. That is our reduction half reaction because it had to gain 3 electrons. To balance it and make them both 6, we'd multiply this by 2, this one by 3. The electrons would cancel, and our balanced reaction would look like this. So to draw the cell, remember the key things that you have to have in your picture. You need 2 half cells. You need 2 electrodes, which are the solids. They need to be connected by a wire, which is where our electrons are going to flow. And you need to put your voltage or voltmeter in the middle there. The electrodes need to be sitting in a solution, so we put a water there to represent that it's solutions. And then you also need your salt bridge so that the ions can balance out and we don't get a buildup of one charge or another. To label it, you tend to put oxidation or the anode on the left side. So this would be our anode, which is where oxidation takes place. So the solid in the oxidation reaction is nickel, and then the ion in solution would be nickel +2. For the cathode, you typically put that on the right side. That is the reduction. The solid in the reduction is cobalt, and the ion is cobalt 3+. For the salt bridge, you would want to show any inert electrolyte. Again, I like just to choose anything from group 1, and then nitrate, because I know that those things are aqueous, so you could really show them as the ions if you wanted to, and they're not going to react with anything. We've labeled the anode, we've labeled the cathode, and then draw the direction of the electron flow. So remember, oxidation loses the electron, so the arrow should always be going from the oxidation to reduction, and it should always be on the wire because electrons flow through the wire. Number 6, draw the direction of the positive ion flow. So we're using up the positive ions. These are becoming solid. So we need to balance that out by replacing them. So our sodium ion would be going this direction. Even though it doesn't ask for it, the negative ion is going this direction because the nickel is going to be adding in a bunch of positives. So we need the negative to help balance that positive out. And then finally, calculate your cell potential. So we're going to use page 23. Now, unfortunately, page 23 does not have the cell potential for cobalt. So that would have to be given to you. And I'm going to tell you that that potential is 1.82 volts. Then we can look on page 23 and find our nickel reaction. Now it is flipped because nickel is being oxidized. So when we go to write our cell potential, we're going to change the sign. And so we're going to say it's a positive 28 volts. And so when we add those cell potentials together, we have a overall cell potential of 2.1 volts. Make sure you try the problems from the textbook and leave any questions you have on the Google form.